So the next time you're in Manhattan, East Manhattan, look for the corner of Bethune and Washington Street and walk down Bethune Street. You'll see this old industrial looking building. It was the old Bell Labs building. And a lot of technologically extremely important experiments took place at one time in that building. Now it's the West Beth Artists Housing Project. But if you look on the wall there in a little tiny alcove out of the way, you'll see this plaque to that experiment. The experiment involved firing a beam of electrons at a nickel crystal. And they looked at how the electrons scattered. What they saw was pretty surprising. They saw interference patterns. Now, you're only going to get interference patterns when you have a wave. So this was experimental, strong experimental evidence that electrons, just like electromagnetic radiation, can behave like waves sometimes and particles other times. In fact, electrons, when they are free, moving freely, they act like particles. But when they are trapped in a small space, they act in a wave-like fashion. Now, before this experiment, this had been suggested by Louis de Broglie. He had presented a relationship that suggested that particles could have wave-like properties. And we're going to study de Broglie's relation in this lesson. And we're going to look at another experiment that showed wave-particle duality in electrons in a minute. Here's a simpler version of the nickel crystal diffraction experiment. We've got essentially a cathode ray here, which is a beam of electrons, and we're going to fire it at a double slit. Now, we'd already done this experiment with electromagnetic radiation, and we saw that the electromagnetic radiation was acting like a wave in this case because we saw an interference pattern here, and we looked at why that happened in a previous video. Now, surprisingly enough, you see an interference pattern with electrons as well. And this is irrefutable proof that electrons are acting like in a wave-like fashion here. But they're also acting in a particle-like fashion too. If you fire the electrons through here one at a time, and you fire 100 through, you'll see that instead of having them all pile up, as they would if they were traveling in a straight line through the slit, they're scattered all over the place. And each electron that you fire through makes a little, a little spot there. And that's a particle-like behavior because the particle is hitting the screen there. But when you fire more electrons, you start to see that they're not hitting the screen in random positions. They tend to be hitting along these lines a little bit more than they are hitting here. And when you fire more and more electrons, the pattern becomes clearer. It is clear that this is an interference pattern. So the electron is acting like a wave in the sense that it produces an interference pattern, and it's acting like a particle because we can see the impact of the particle on the screen. Well, now what is this wave made out of if the electron is acting like a wave? I mean, you know what a water wave is. It's the water level rising and falling makes the wave. And even an electromagnetic wave is easy to understand what the wave is. It's the electric field rising and falling, and also at right angles, the magnetic field rising and falling. But what's rising and falling here? Well, it turns out in an electron wave, the amplitude of the wave has to do with probability. It has to do with the probability of where the electron is located. So this is a probability wave that we're seeing. And the electron is the probability wave.